Making an ion from an atom and figuring out the electron configurations is actually not that bad. So let's talk about anions first, the negative ions. And an anion just has extra electrons beyond what the neutral atom would have. And adding electrons to make the anion is pretty easy. You just follow the normal N plus L rules of filling in electrons. So let's make the phosphide ion, which is P negative 3. So phosphorus is neon 3s23p3, but like we talked about, the 3 P's can hold up to 6 electrons. So when you make phosphide, you have an extra 3 electrons. Remember, phosphorus in group 5 minus 8 has a negative 3. The negative 3 means 3 more electrons, and they are just going to go in that 3p configuration. So phosphide would be neon 3s23p6 or argon. Notice how we went from a paramagnetic atom to a diamagnetic anion. A lot of the common anions and cations are actually going to be noble gas configurations and diamagnetic, which is kind of cool. So if you're making an anion, just add the electrons as if it was normal. All right, just add them using normal N plus L rules and you're good to go. Cations, the positive ions of the atom, all right, what you want to do in these cases is you're going to take away electrons from a configuration. And the rule is a little strange. I want to focus on that. You want to take it from the highest N, and if there's a tie, then you take it from highest N plus L. Phosphorus does make a positive 3 ion. It's rare, but it does happen. And to make a positive 3, you have to remove 3 electrons. So in this case, you could remove electrons from highest N. So if phosphorus has 1s2, 2s2, 2p6, 3s2, 3p3. But the highest N would be the 3s and the 3p. Those are higher than the 1 of 1s or the 2 of 2s and 2p. So we're going to remove the electrons from 3s or 3p, but there's a tie. All right, which of those 3s do we pull them from? So the second part there says if it's a tie, highest N plus L. Highest N plus L basically means that last one's in equal first one's out, but in this case, 3p would be higher N plus L than just 3s. So for either way, you want to take them away from the 3p. Phosphorus 3 plus would be neon 3s2. So again, on the left-hand side is neutral phosphorus, and the question is, where do you take away those 3 electrons from? And it's definitely going to be highest N, so 3s or 3p, but which one? So if it do have a tie, then you take it away from highest N plus L. So highest N plus L would be the 3p's. You can see that that's empty on the right-hand side. You end up with 1s2, 2s2, 2p6, 3s2. The electron configuration 1s2, 2s2, 2p6 represents which ions and or atoms. All right, and this is kind of interesting. Got sodium, got oxide, magnesium 2 plus, and neon. Well, let's start with neon. All right, so neon has 10 electrons. Its atomic number is 10. And if you put the electrons in, first electrons go in 1s, next electrons go in 2s, and then 2p. So 2 plus 2 plus 6, the superscripts of that configuration equal 10. Neon is 1s2, 2s2, 2p6. So at the very least, then we know that answer D here is legit. But let's look at the other ones. Now, sodium, neutral sodium, has 11 electrons. And neutral sodium would be 1s2, 2s2, 2p6, 3s1. But sodium plus 1 means we're taking away an electron. And you take it away from highest N, or highest N plus L. 3s is higher than 2s and 1s and the rest of sodiums. So the sodium plus, we're going to take away that 3p1. And guess what? Sodium plus 1 is also 1s2, 2s2, 2p6. So now you can see that at least A and D are correct. You're going to find here that all of these have the same configuration. So let me save you having to watch my bad handwriting and look at what's actually over here now. You can see that when all is said and done, they're all 1s2, 2s2, 2p6. So here's sodium. We're taking away that 3s1 electron to make it Na+. Let's go to magnesium here real fast. See, magnesium has a 3s2, but we're taking away 2 electrons. Highest N means take those away. Also 1s2, 2s2, 2p6. Oxide, which I saved for last, you're adding 2 more electrons. It has a negative charge. You're going to put them in the lowest unoccupied orbital first. 2p holds up to 6. Oxide also is 1s2, 2s2, 2p6. They're all the same electron configuration. A lot of the noble gas configurations are very common when it comes to main group ion charges. So the positive ones like sodium, magnesium want to be like noble gases, and the negative ones like nitride, oxide, fluoride, chloride, they also want to be like noble gases. Noble gas configurations are the cool kids in the back of the bus. All of the ions kind of want to be like them. Transition metals, when you're making an ion, and these will almost always be positive, I want to go back to the idea where you remove the highest N electrons first and then the N-1 electrons after. Now, before so far, when you've made a positive ions, it's always worked out that the last electrons in are the first electrons out. But you don't necessarily see that with transition metals. And let me show you an example. Iron, neutral iron, is argon 4s2 3d6. And the two most probably stable configurations of ions for argon are iron 2+ and iron 3+. Now remember, the rule is remove highest Ns electrons first, and then after that, if there's a tie, go highest N+L. Well, iron has 4s2, and 4 is higher than 3. So what that means is that the first electrons out for transition metals always the 4s2 or 5s2 for the next ones, or 6s2. So iron plus 2 has an argon 3d6. None of the d electrons were touched. If you make iron 3+, then you take away one of the d electrons, because then you've got a tie between 3d, 3p, 3s, etc., etc. I'm pointing this out because when it comes to transition metals, the last electrons in are not necessarily the first electrons out. So in iron's case, 4s came out before 3d, even though as you're filling the electrons in, the 3d electrons were filled in after the 4s, which is very wild. Here's orbital box notation. Our iron 4s2 3d6 becomes just 3d6 when you have the iron 2+ ion. And if you make, of course, iron plus 3, then you have 3d5. So again, always remove electrons from the highest N value first. And that usually means the s electrons before the d's you just finished putting in. Notice how the magnetism changes quite drastically. So for example, the iron and the iron plus 2 would both have 4 unpaired electrons, but iron plus 3 would have 5 unpaired electrons. Hund's rule, keeping all of them separate as long as you can. So iron plus 3 would be very paramagnetic. More unpaired electrons means more paramagnetic. And this is basically saying what I just said, so I guess I just couldn't wait. Anyway, the number of unpaired electrons as it goes up, the degree of paramagnetism also increases. All right, so here's zinc plus 2. We're removing the 4s electrons first because highest N before lowest N, but zinc plus 2 is diamagnetic. It has a 3d10 outside of the argon core, totally diamagnetic. On the other hand, iron plus 2 has 4 unpaired electrons, which does make it paramagnetic. Here's an example of manganese 2+. Manganese 2+, you remove the 4s electrons as well, and you end up with 3d5. So if I asked which of those ions was the most paramagnetic, you would say that manganese 2+ was the most paramagnetic. Usually the more unpaired electrons you have, the more paramagnetic something is. And of course, zinc as a diamagnetic system wouldn't be magnetic at all. It would be the least paramagnetic or non-magnetic, something like that. Which ion corresponds to this configuration? So notice that there's no 4s electrons. All right, so this is going to be an ion because the 4s electrons get filled in first, but if they've moved away, then it's going to be taken out. And there's also some 3d electrons. And if you count them up, 2 in the first box, 4 in the second, 5, 6, 7, 2, 4, 5, 6, 7. This is a 3d7. Now, having an electron periodic table here can be super helpful. And what I'm going to do is I'm literally going to start counting at scantium, SC number 21, because scantium would be a 3d1. Titanium would be 3d2, vanadium 3d3, chromium 3d4, manganese 5, iron 6, cobalt would be 3d7. So neutral cobalt would have a 4s2 3d7 configuration. But because cobalt here in answer C has lost 2 electrons, that's going to keep the 4s orbital empty. So I'm going to argue that answer C would be correct. And if you actually figure out the values, here they are. One thing to note is that rhodium is actually on the next row down. Rhodium would have 4d electrons, but it wouldn't have an unfilled 3d set. Rhodium would have a 3d10 configuration. And of course, calcium would be just argon, stuff like that, which is crazy. Another thing too, rhodium is another one of the weird exceptions on the N plus L rule. Rhodium is actually krypton 5s1 4d8, fascist krypton. Up there I wrote it as krypton 4d6. All right, and again, either way, or neutral rhodium would be, neutral rhodium would, I wrote down as krypton 5s2 4d7. Neutral rhodium is actually krypton 5s1 4d8. This is again chemists' inability to understand totally what's happening. N plus L, which is what we are using, works pretty well most of the time, but there are some exceptions, fascists. However, as an ion, you could use either configuration and end up with the same result, which is also good. But that's neither here nor there. The important part is that you saw that in this problem, you had an argon 3d7 configuration. Because the 4s was empty, the 4s electrons had to be removed. And what I literally did is I just counted left to right from scantium 3d1 over to cobalt 3d7, and because that cobalt without 2 electrons would have an empty 4s, cobalt 2+.